We're now coming to the last part of the lecture. So we spent some time talking about basic fundamentals of modern physics, electromagnetism, and quantum mechanics. And then we had 3 lectures on particle physics. And well, without labeling it so, these 3 lectures basically introduce systematically the standard model and all the problems with the standard model. And now that we've got ourselves oriented in how to think about particle physics, the whole rest of the time we're going to talk about gravity and why gravity is so much different. So to start off, I thought I would spend the lecture just basically reviewing and going over Einstein's picture of gravity. And so this lecture will have a lot in common with the first one. Probably a lot of things that many of you know, so hopefully it's still interesting. But I wanted to cover a lot of these things in order to emphasize a few important physical points behind Einstein's gravity as a lead into the next lecture, which is probably going to be my favorite one, which is a general lecture on why quantum gravity is so hard. And then only after that, when we talk about the problems of quantum gravity on their own, we'll introduce string theory and why string theory is a candidate for dealing with those. I think it's important to identify what the difficulties of quantum gravity are in general before talking about what this proposed solution to them is and its own problems. Yeah, shoot.
Is there going to be a hiatus for Memorial Day weekend?
Oh yeah, thank you. I should mention that. So this lecture is next week. This is 2 weeks from today, and then there's Memorial Weekend. Next time I'll put dates on here. This Memorial Weekend is nothing, and this lecture is June 2nd. So there is no lecture on Memorial Weekend. Unfortunately, we did schedule a lecture. This lecture, I think, is this one. We did schedule a lecture that will be during this NATO summit. Nobody thought about that. So it'll be interesting for me to get there too. Okay, so today is all about gravity, and I couldn't resist putting some picture of a guy sitting under an apple tree. My friends in Cambridge, it's funny, I've been to a lot of the places where physics is done, but I've actually never been to Cambridge. But I have friends who are there, who have been through there, and they tell me there's an apple tree there that they call the Newton apple tree. Okay. It is the most prevalent fundamental force of nature. We see it at very large distance scales. We see evidence of gravitational interaction between planets separated by planetary distances, galaxies separated by galactic distances. And part of the reason for that, we don't see electromagnetism operating at such large distance scales. And that's essentially because electromagnetism has this notion of positive and negative charge. Like charges repel, opposite charges attract. But on the whole, most of the things in the universe are largely electrically neutral. So these two guys don't have an appreciable electromagnetic force between them because they're, roughly speaking, electrically neutral. But everything interacts with gravity, and everything interacts the same way. Gravity is attractive, all things attract, so even though these guys are electrically neutral and don't have a big electric force between them, they do have a gravitational force because there's no notion of plus or negative charge that can cancel each other out. All massive bodies attract each other, and so gravity is a long-range force that's felt really over long distances. And this takes us to a new regime. Throughout these lectures, we've been talking about physics and seeing how weird it looks in regimes that are different from those of our everyday life. Whether it's regimes of moving very fast, or looking at very high energies, or very short distance scales, physics looks weird. And gravity allows us to, or forces us to think about distances that are very large, much larger than what we're used to in everyday life. So there's a long, long history of people thinking about gravity because we see it in our everyday life so readily, even before modern technology. Introduced electromagnetic, we see gravity. Ancient philosophers thought about gravity. I don't want to dwell too much on the history of gravity. I'll jump right in with Kepler, who observed the motions of the planets and came up with 3 empirical laws to describe planetary motion. And I'll just state what they are. The orbit of every planet is an ellipse, not really a circle. The orbits sweep out equal areas in equal times, which is just a statement that a planet, the time it takes for it to move along this little bit of path, which sweeps out this area in its orbit, where this is the sun, is the same as the amount of time it takes to go in this little path. And then he made some observation about how the period of the orbit is related to the size of the ellipse. This semi-major axis is just a way of characterizing the size of the ellipse. So these were just 3 empirical laws that described how people had observed the motions of planets. And Newton came along and introduced the idea of the universal gravitational force that describes all of them. He said if you have 2 massive bodies, say the sun and the earth, and have mass m1, sun has mass m1, the earth has mass m2, They attract each other, and they attract each other with a force that's proportional to the masses of the two bodies and inversely proportional to the distance between them squared, with some coefficient that we now call the Newton constant. And based on this simple idea that there is a force between massive bodies, Newton was able to essentially derive all of the empirical observations of Kepler. And so this one simple idea was able to describe all the observed motions of the planets in the solar system, and as well as the fact that we experience gravity ourselves, because we experience gravity ourselves. So now the Newtonian framework of gravity has two key features that I'm going to want to spend some time on today. One of these features is action at a distance, and the second is the equivalence principle. Action at a distance is a phenomenon that's inconsistent with relativity, and we'll have to throw it away at some point. But the equivalence principle is one of the deepest properties of the world in which we live, and I want to spend some time going over that in some great detail. But I'll start with the first one. The idea of action at a distance comes from the following. Suppose that the sun is just sitting here, but the sun periodically will eject matter. There'll be ejections of stuff that shoots stuff away, so it might eject some matter away. And when it ejects that matter away, this equation tells us the force that we feel from the sun should change. Now, you can ask the following question: at what point do we know that the force that we feel from the sun changes? If we could measure sensitively enough to be able to tell the difference between the force when it has mass m1 and the force, say, when this other stuff gets ejected is over here, at what point would we detect that this force has been changed? And in Newtonian's system of gravity, well, okay, and for that matter, you can ask, how do we know? How do we even know that this happened? You know, how do we know that the force changed? What tells us that the force changed? How is that information carried to us? And in the Newtonian framework of gravity, the Newtonian framework of gravity posits a mechanism called action at a distance, which is essentially the statement that as soon as anything changes on the surface of the sun, or the sun ejects matter or anything else, the force that it exerts on all objects is changed instantaneously throughout all space. Which is to say that as soon as this bit of mass is ejected from the sun, we instantly know about it, and the force we feel instantly changes. The gravitational force in Newtonian gravity is not mediated by anything. The interaction is instantaneous, even across great distances. And we know for a fact that this is not consistent with relativity. We've seen throughout these lectures that nothing can move faster than the speed of light, information cannot move faster than the speed of light, and there's no way that we can learn that something happened over here at the sun faster than light would be able to carry that information to us. So this whole idea of action at a distance is horribly inconsistent with relativity, and will have to be replaced by something. There will have to be some way, some mechanism to carry the information about the changing mass distribution of the sun over to us. And at the end of the lecture, we'll come back to that and discuss what that mechanism is. But before we get to that, I want to spend all of the interim time on the second main feature of Newtonian gravity, which is the equivalence principle. And the equivalence principle basically follows from this simple type of equation. This equation is an equation for the force that acts on the body M2. So there's a gravitational force, as we said, from Newton's universal law. There's a gravitational force that's proportional to the mass of the sun, the mass of the body, and inversely proportional to the distance squared. And this fits the astronomical observations very well. But then there's the second equation here, and this is just a definition of what a force is. What is a force? A force is just, a force is an action that you perform on a body to change its state of motion. If there were no sun here, we wouldn't want to rotate around the sun. We just want to move in a straight line. The sun has to push on us to make us change our motion. And what this equation tells us is that the rate at which we're accelerated inward by the sun is determined by not just the force that the sun acts on us, but also by our mass. So there's two notions of mass that are appearing in this formula. One of them is the inertial mass, and that's what's sitting here. And that measures how much force we need to accelerate the Earth. So an object's inertial mass is a measure of its resistance to changes in its state of motion. We want to go straight. In order to accelerate us towards the sun, you have to exert a force, and the inertial mass tells us how much force is needed. So it's really a statement about a body's motion and how it reacts to forces. The mass over here is a different kind of thing. It's essentially the charge under the gravitational interaction. It tells us how strongly different objects interact with gravity. And the fact that it's the same mass appearing on both sides is the statement that the inertial mass of an object is the same as its gravitational mass. That's, I should say again what that is. It's the statement that the strength with which gravity couples to a given body, like the Earth, is determined by this fundamental property of that body, which is its resistance to changes in its motion. This is a very, very deep observation about the world around us, so I gave it its own slide, just to emphasize how important this is. You know, the inertial mass and gravitational mass are really two fundamentally different concepts in principle. This having to do with resistance, you know, how much force you have to act on a body to accelerate it, and this having to do with how strongly a body interacts with gravity. They didn't have to be the same, and they certainly, you know, the similar statements certainly do not exist for the other forces. The other forces, you know, the electric force, the charge of an object was arbitrary. The charge of an electron is 1, the charge of a quark, one of the kinds of quarks, is 2/3. Those are just sort of arbitrary numbers. This is not arbitrary at all. Gravity couples to everything in the same way, and it couples according to that body's inertial mass. And a consequence of that is that gravity accelerates everybody at the same rate. So if I come back to this equation, I've eliminated the F term in the middle here. I can cancel off, you know, because I've said that the inertial mass, which is the guy sitting here, and the gravitational mass, which is the guy sitting here, because I've said that those are the same, I can just remove them. And they should remove, there they go. And discover that really what Newton's law of gravity says is that an object like the Earth is accelerated in a gravitational field. And it's accelerated in a way that depends on a fundamental constant of nature, the distance from the massive body and the mass of the massive body. But it doesn't depend at all on the mass of the Earth. So any object that I put here, whether it be the Earth or anything else, will feel the same rate of acceleration in this gravitational field. Everybody is accelerated at the same rate. This is a very, as I keep saying, it's a very deep property of the world in which we live, that gravity accelerates all objects at the same rate. And because of that, it's important to make sure that it's really a true property of our world. So you can ask a very important question, which is, you know, this is a very, almost you would say, counterintuitive statement. How do we know that this is true? How do we know that everything is accelerated at the same rate in a gravitational field? Well, we could try dropping stuff off the Leaning Tower of Pisa, and that's the famous story of what Galileo did. I don't really know if this happened or not. I know it's a thought experiment he wrote about. I don't know if he actually did it. But if everybody is really accelerated at the same rate as they move in a gravitational field, then if you drop two objects of different weight from the top of the Leaning Tower, they should fall at the same rate and hit the ground at the same time. Of course, there are problems with doing this experiment in practice. You encounter issues of air resistance. If you drop a feather at a stone, the feather is obviously going to take longer to fall because it's going to suffer more effects from air resistance. It's also not so easy to make accurate measurements at the time of flight. You know, the two things, if they don't hit the ground at exactly the same time, at a slightly different time, how precisely can you measure that? So, like I say, I don't know if Galileo really did this experiment or not, but the experiments Galileo did do involved pendulum. So a pendulum is, well, here's a picture of a pendulum. You basically, it's like there's a pendulum on a clock. And if it's true that every object is accelerated at the same rate in a gravitational field, then the period of the pendulum shouldn't care about the mass of the bob that you put on the end. So you can put a bob with mass 1 on here and a bob with mass 3 and try to measure the period. The other advantage to an experiment like this is that if I put bobs of two different masses on the end, the difference in the periods that I'm sensitive to is not that small. But I can allow the pendulum to swing back and forth for a long time. So instead of comparing the time it takes to do one trajectory, I can compare the time it takes to do many, many, many trajectories. And if I look at the time it takes to do, say, 100 back and forth things for bobs of two different mass, I'll be sensitive to much smaller differences in the period of the pendulum. So this kind of setup allows you to measure the equivalence principle much more precisely. Now, this question is so important that people are still doing experiments to test it today. And those experiments are based on a torsion balance, and I may or may not have had a cartoon of this particular torsion balance in the first lecture. I think I did. I might have taken it out. These types of experiments are all based on the ideas of Woodbush, if I'm pronouncing it correctly. And the idea of the Woodbush experiment is roughly the following. So I have a string that's being suspended from some apparatus up here, and I put two masses on it, and these masses are different, and these masses feel two forces fundamentally. They both feel the force of gravity pulling them down, but they both feel a second force that plays an important role. And that second force is this thing, the centrifugal force. And you might yell at me and say that the centrifugal force is not a real force, it's an apparent force, and that's true, but it is a force that we feel in our everyday life because we are in an accelerated frame of reference. The Earth is moving around in a circle, and because the Earth is moving around in a circle, there's a very tiny force that objects feel due to the fact that we're in an accelerating frame that points out away from the circle. And that's what these forces are. And if you go through the analysis of the system, you'll see that if gravity wants to accelerate both of these masses at the same rate, then the effect of the centrifugal force is just going to be to take the bar, the two masses, and just sort of uniformly move them both at the same time. But if there's the slightest discrepancy between the acceleration that gravity wants to do on this body and this one, then in addition to sort of swinging up a little bit from the centrifugal force, the rod will begin to rotate a little bit. It'll rotate, one of them will move down rather than the other. And you put a mirror here, and shine a laser on it in order to detect that relative rotation, and you can measure very precisely what the difference between the inertial and gravitational masses could be. So people have done this kind of experiment. The group I'm aware of is at the University of Washington. They're really sophisticated experiments people are doing, and so far no deviations of this have been found. So we really do believe this is a fundamental property of the world in which we live, that gravity accelerates all bodies at the same rate. Emphasize again, gravity accelerates everything at the same rate. It is a deep property of nature. It has profound consequences. In principle, it's already there in Newtonian gravity, but that's where this guy comes in. This guy took this observation and just ran with it. And, well, he did what Einstein always does, always did. He came up with a very clever series of thought experiments that taught him some very interesting and new things about the world in which we live. Okay. So, what can we say about gravity, knowing that gravity accelerates everybody at the same rate? Einstein said the following: since gravity accelerates all bodies at the same rate, he could cook up two different observers who could not distinguish themselves from one another. So one, you can imagine a guy that's sitting in a closed box in a gravitational field. So we put this guy in a box and we strand it in the middle of some, I don't know, some grassland or something. And, okay, the guy in the box can tell he's in a gravitational field. He feels a force. He knows gravity's pulling him down. Okay. And the other observer is a guy who's sitting in a box, and that box is in outer space, where there is no gravitational field, but he's got a rocket on his box, and he's accelerating at a rate that's the same as the rate that gravity would have accelerated in here. So Einstein said you cannot make any distinction between these two frames of reference, and you can clearly see that in here you're going to feel a force pulling you down, and here, because the thing's accelerating up, you're also going to feel a force pulling you down. So that doesn't sound so crazy, but no. So yeah, that's what I'm saying here. You cannot tell the difference between being stationary in a gravitational field or being in an accelerated frame of reference, which is what this guy's doing. So now I'll get to the next bit. So obviously these guys both feel the force, but any experiment that they're able to do in their box will not be able to tell them whether, so this guy cannot do any experiment in his box, say from cutting a hole in the box and looking outside. He cannot do any experiment in the box that can tell him whether he's in this situation in the middle of some grassland somewhere, or in this situation out in space accelerating. And, a simple experiment you might imagine is taking a ball and dropping it. And, well, if gravity accelerates everything at the same rate, so this ball is going to fall at the rate g, the same rate that he would fall if he jumped up and down. And over here, what rate is the ball going to fall? The ball's going to fall at rate g because, well, the ball really just sits there, but he's accelerating at rate g in this direction. So because gravity acts in the same way on everything, accelerating everything at the same rate, any experiment this guy does is going to have the same result as the experiment that this guy does. Now, Einstein's thought experiments also, Einstein likes to use a slightly different setup, which isn't necessarily a guy sitting in a gravitational field, but Einstein likes to think about free-falling observers and inertial reference frames. So, equivalent to the last situation, you can can also argue that these two observers can't distinguish anything. So on the one hand, you have an observer in a box that's been taken up in an airplane, and then his friends dropped him out of the airplane but let him free fall, and well, something happens out here, but we'll pretend that never happened. So we have a free-falling observer, and this free-falling observer is going to feel weightless. The box is accelerating at the same rate as everything else, so this guy feels completely weightless. And the other observer is an observer sitting in a box that's floating out in free space. And the equivalence principle tells us that these two guys can't tell the difference between each other. Any experiment this guy does is going to have the same result as any experiment this guy does. Because to this guy, there's no forces acting on him. I mean, you can just imagine how you feel in these amusement park rides where they put you in and they take you up on some big high tower, and then they make you sit there and get real nervous, and I really hate that part. And then they just drop it, and you feel weightless. You feel like nothing's acting on you. Okay, you feel the wind because there's wind, but you feel weightless. And yeah, so this guy feels like no forces are acting on him at all, and same as this guy. So Einstein put forward a version of the equivalence principle, which he called the strong equivalence principle, which is the statement that neither of these guys can perform an experiment that could distinguish between being in a box free falling or being in a box in the middle of space. Okay. So this idea that a free falling observer is the same as an inertial observer is the foundational idea of general relativity, which is Einstein's theory of gravity. It's the foundational principle. You can say it a couple of ways. An observer cannot tell if they are being acted on by gravity. This guy is in a gravitational field falling, but he has no way to tell that he's being acted on by gravity. He has no way to tell that he's being acted on by his force. The only reason we know that gravity is acting on us, we're in a gravitational field, but the only reason we know gravity is acting on us is not because we're necessarily sensitive to just the pull of gravity, but it's because the Earth is pushing us up to keep us from falling further in. So if we didn't have the Earth there to push us up from underneath, we would also have no idea that gravity was acting on us. This guy could not tell that gravity was acting on us. Or, said a different way, a free-falling frame is indistinguishable from an inertial reference frame, which is one where you're just moving along and no forces are acting at all. So this is the important idea of general relativity. And Einstein used this idea, before he developed the general theory of relativity, he used this idea and thought experiments based on this idea to derive some very surprising and interesting ways that gravity behaves in our world. And what I wanted to do in the next 15 minutes or so is talk about how you can sort of use thought experiments, go through Einstein's thought experiments to understand these odd features of gravity before getting into a full discussion of general relativity in earnest. So that's this bit. We will come back to the geometric meaning of this, which everybody knows this is leading to geometry. We'll come back to the geometric meaning of this in a minute. For now, I want to focus on some physics. So the first weird property of gravity that I want to talk about has to do, well, all of them have to do in some sense with gravity and light. And I want to imagine the following setup. We take our guy in the box, we set him up here next to the top of some building, and we're going to let him drop. But at the instant that he drops, his friend who's on the building shines a light in the box. And the question we want to ask is, what does the observer in the elevator see? And what does the observer on the building see? And I'm calling the box an elevator because Einstein always talked about free-falling elevators and so on. Yeah, okay. So here's the setup. We're going to shoot the light inside, and the light enters the elevator. So the observer sees light entering the elevator. Now, Einstein's strong equivalence principle says that this guy has to see things the same way that this guy would. So that's why I have this little cartoon of the inertial frame up here. It's just to remind you that this guy cannot tell the difference between being in a free fall situation or just being, sitting floating in empty space. So over here, this guy sees a light shined into the elevator. So obviously, he's going to see the light travel in a straight line. So if this guy saw anything other than this light beam traveling in a straight line, he would be able to use that to tell that he's in a gravitational field and not in an inertial reference frame. So, by Einstein's strong equivalence principle, this guy also must see the light traveling in a straight line. But because this guy is falling, when the light reaches the other end, he's fallen a little bit. So the trajectory of the light that he sees is the straight line trajectory. And the point that he sees the light exit the elevator is here. But our friend on the building sees this point as lower than the point that he showed it on. So the trajectory that this guy sees the light follow is one that's falling. Basically, I can say that in a much more concise way. This observer needs to see the light move in a straight line. So this one must see the light falling with the elevator. So if the light's moving in a straight line from the perspective of the falling elevator, then the guy who's outside must observe the light falling in the elevator. So just by saying that this guy has to see things the same way that this guy does, or that there's no distinction between a free-falling observer and an inertial observer, we see that the path of light must be bent by gravity. So this was a very surprising prediction when Einstein made it in the early 20th century. People were extremely surprised by this. And it was the verification of this fact that made Einstein a national hero or whatever. This is the thing that really made him famous. So that's one property, gravity bends light. You can do another experiment involving shining a light from the bottom of the elevator. This one's a little trickier. So now I'm going to put two people on the top. I've got one person down here who's going to shine a light at the bottom of the elevator right at the second that it falls. And by the way, I have to say, I've changed the discussion of this since I made the handout. Unfortunately, the handouts have to be in by Thursday morning. And I've since realized the discussion of the handout's not very good, so I apologize for that. I will fix the handout, and the version that shows up on the internet will be the fixed version. So, so we imagine that this guy shines a light into the bottom of the elevator, and then there's another guy up here at the top who's going to observe it when it comes up the top. So over here, our friend in the inertial frame sees, if everything this guy sees is the same way this guy sees it, this guy sees a light wave come up the bottom of the elevator and sees it travel to the top of the elevator. That's a very ordinary thing. He just sees light, somebody flashes a light at the bottom, goes up to the top. Nothing special happens. So in particular, this guy thinks the wavelength of the light is the same when it gets to the top as it is when it shoots in the bottom. Yeah. The way we can think about that is he sees the same amount of time between peaks of the light as it comes in the bottom and it goes to the top. Now, in order for this guy to see the same amount of time between peaks of the light at the bottom and the top, it must be that by the time the light gets to the top, the peaks are further spread out from this guy's point of view. Why? Because the time it takes the time that this guy's going to see between peaks is shortened because the elevator is moving down. Because the elevator is moving down, he's going to see less time between these two peaks than this guy will, because he's actively moving in the direction from one peak to the other. So, in order for this guy to see the same wavelength, the same amount of time between peaks at the bottom and the top, the wavelength of the light from the point of view of the observer outside must have increased. So this is a statement that light undergoes what's called a gravitational Doppler shift, or that the wavelength, as it climbs out of the gravitational field, spreads out. So there's a nice picture of this on Wikipedia, and it looks like this. If a massive body emits some light, the wavelength that we observe out here is longer than it was when it was emitted. Now, this leads indirectly to the third weird property of gravity that I wanted to get into. It's a little bit indirect, but I'll talk about it in this way, and that is the so-called gravitational time dilation. So you can imagine that a radiation is being emitted by our favorite atomic clock. So we put an atomic clock here. Now, how do atomic clocks work? Well, atomic clocks measure oscillations of atoms, like the cesium atom, for example. And the period of oscillations of the cesium atom is a very fixed time, and that becomes the standard of time. And, well, if we look down at the radiation coming from that clock, we're going to measure a longer period of time between pulse at peaks than the observer down here will. So this time between peaks is, we think, the time between oscillations of the cesium atom, which is a fixed unit of time. So because we've measured the time between peaks to be longer than they really are down here, we conclude that this clock, which is based on that time between peaks, is running slower. So I said that very poorly, but hopefully you get the idea. The time between peaks here is the fundamental unit of time, as determined by this atomic clock, and we see the time between peaks associated with this clock to be longer, so it means we see the fundamental unit of time, the fundamental second of this clock, to be longer. So time is actually dilated by a gravitational field. Now that's gravitational time dilation. So this simple idea that Einstein pointed out, the fact that an observer in free fall is indistinguishable from an observer that's just sitting in an inertial reference frame floating in space, leads to three dramatic implications that are all very weird and you wouldn't otherwise expect to come from gravity. One is that gravity bends light. The second is that gravity bends the frequency of light. And the third is that gravity actually warps the passage of time. So these are three very, very crazy phenomena about the way that gravity behaves in our world. And Einstein very famously predicted all of these before formulating his full general theory of relativity. So before getting to the theory of general relativity, I want to just comment, these are all really great. They all follow from these nice thought experiments, but remember, an assumption went into these thought experiments. This assumption here, the free-falling frame is indistinguishable from the inertial frame. This is an assumption, and if the assumption leads to weird conclusions, then we should only believe them to the extent that we can verify them in nature. Maybe the assumption's wrong. So it's important to ask, how are these things actually seen in nature? And I want to take a minute to review sort of how people found all these things. So the bending of light was verified allegedly, and I think there's, okay, I don't want to get into it, but I'll just say it was verified, and people have gone back and looked and wondered whether this guy was propagandizing or not. I don't know, but it was essentially verified during the Eddington expedition to Principe, I think, island off the coast of Africa, during a solar eclipse. And it was this verification that really made Einstein extremely famous around the world. So the idea is essentially the idea of gravitational lensing that I described last week. That if light if light is bent by matter, then the presence of matter between us and a distant object can change where we think the object is. So if you imagine there's a star here, and when the sun is over here, or when we're over here looking at the star, then we don't have any problem. We just look at the star and we see where it is. But if the sun is between us and the star, then it's going to bend the light. And if we don't account for the fact that the light is bent, we're going to think that this light actually came from here. When we look out at the sky, we think the light coming to us comes in a straight line, so if we measured where we thought the star was without accounting for the fact that the light was bent, we would think it's here. Now, it's very hard to, this effect is prominent when you're looking at stars when the sun is in between us and the stars. So when you're looking at stars during the daytime. That's very hard to do because the sun is very bright, and that's why Eddington did this during an eclipse. So during an eclipse, the sun is eclipsed out, and you can look at the positions of stars that are nearby. And they knew where these stars were supposed to be. They knew where they appeared to be during the eclipse, and they weren't in the same place. And this verified that light was really bent by the sun. Now, I should mention that based on the simple elevator arguments that I gave earlier, those simple arguments, which eventually lead the idea of just curved space, gave Einstein the wrong answer in 1909. He didn't get, now this happened in 1919, so he had it right before the observation. Einstein didn't get the right answer until he developed the full theory of general relativity, which extends what I said to space-time, and I'll come back to this later. So Einstein even got it wrong at some point, but he had the idea right, that light is bent by gravity. So the second I want to talk about is the gravitational redshift, or the fact that gravity changes the frequency of electromagnetic radiation. And this is just an amazing experiment. And I put this on here because it's an excuse to put a picture of this building. This is Jefferson Lab. This is where the physics department at Harvard. I used to have an office right there. And you'll notice there's no window there, but there are these really lovely skylights. At the time, I thought, wow, okay, office has natural light. That's no big deal. I didn't realize what a wonderful thing it is to have an office that actually has natural light. Because most, you go on to do postdocs or whatever, most postdoc offices are closets. So didn't appreciate how nice this was, so I get a little nostalgia. But everybody at the department talks about this building, and this particular famous experiment done in this building. What these folks were able to do, Pound and Rebla, they were able to accurately measure the change in the wavelength of photons due to the effect that, due to the difference in the gravitational field at the top of the building and the bottom of the building. So they were essentially sensitive to the fact that the gravitational field of the Earth is a little bit weaker here than here, over a distance of 22.5 meters. just the idea of that is incredibly impressive to me, how you could be sensitive. I mean, it is incredible. And the way they did their experiment was really kind of cool. They used a thing called the mouse power effect, which I'm not much of an expert on, but I'll say a little bit. They put some sample of iron up by the roof, and they put some sample of iron at the bottom. And this iron was such you could stimulate it to emit photons. And the photons come out at a very sharp wavelength, a very particular wavelength. And the iron down here can reabsorb those photons, but only if they're at just the right wavelength. So if the wavelength of this photon is changed even a little bit, then when it gets down here, the iron won't be able to absorb it. And it turns out that even though the difference between the gravitational field here and here is very weak, the shift is enough that if you just send the photons down here, this iron is unable to absorb it. Its wavelength's changed enough that the absorption can't happen. So then what they did was they put a loudspeaker under the iron down here. You know, they'd like to be able to see how much it shifted by. So they need to figure out when the iron can absorb it. So you can't change the frequency of the photons coming down. This is what it is. But you can change the apparent frequency that these irons see by taking the sample down here and moving it up and down. So they put a loudspeaker under it, maybe and shake the thing up and down, and they could see that at some point during the up and down motion, it was actually able to absorb the photons. And based on this, they were able to compute the shift in the wavelength of these photons due to the gravitational redshift. An incredibly precise experiment that people still talk about in this building all the time. It's very thick. So that's a tough one. Gravitational time dilation, which in some sense sounds familiar, is in fact, at least to me, it's the one that's the most straightforward to measure in everyday life. You just take an atomic clock and put it on a plate. And people have done that, and the clocks run differently. I should also say that the GPS satellite system accounts for gravitational time dilation. If it didn't, then it wouldn't work. This is actually one of the effects that this opera experiment that was measuring neutrino velocities had to worry about. They're trying to compare the time that neutrinos left Switzerland and the time that they arrived in Italy. It's a very tough measurement to do, and you need to make sure you measure those times exactly right, and this is an important effect to take place. Another thing that I found pretty curious is that there's a difference between the running of the US and UK clocks. So the official atomic clock of the US is at NIST, the National Institute of Standards and Technology in Boulder, Colorado, which, well, why do they put it in Boulder, Colorado? I can only imagine because it's one of the coolest places in the country. It's also a beautiful place. Just look at that. It's great. So, but the side effect of being in Boulder is it's over 5,000 feet above sea level. The official UK clock is in the Royal Observatory in Greenwich, which is practically at sea level. And because of this difference in elevation, it's actually known that the clock in the UK runs about 5 microseconds slower than our clock per year. So this is a very real effect that we really see without too much problem. So Einstein was able to show, even before developing his full theory of general relativity, just based on the equivalence principle and his strong version of it, that light is bent by gravity, the wavelength of light is shifted by gravity, and time is warped by gravity. But this wasn't enough. This wasn't a consistent theory of gravity. This was just some observation of some things that gravity had to do. The full theory of gravity required some kind of foray into geometry, and that's what I want to get to a little bit next. So, we'll come back to, again, this same thing which I'm harping on over and over again, but just because it's so important. A free-falling reference frame, somebody free-falling in a gravitational field, is indistinguishable from an inertial reference frame, which is, again, the statement that this guy and this guy can't tell the difference between each other. This guy can't tell if he's moving in a straight line, or if there's a sun here and he's moving in a curved line. No experiment he does can tell the difference between the two. So, the effect of gravity has, since this guy doesn't feel gravity at all, he's not sensitive to the fact that he's in a gravitational field at all, the only effect of the sun being here is just to change the path that he takes. It doesn't change anything that he feels, any experiment he performs in his box, it just changes the path that he follows. So the effect of gravity is just to replace a straight line path with a curved path. That's all. It doesn't do anything else. Now, these two observers both think they're exactly the same. They feel everything the same. No experiment they can do can distinguish one from the other. And an inertial observer that doesn't feel a force acting on them always thinks they're moving in a straight line. If I'm sitting in space and I don't feel a force acting on me, I'm going to assume that I'm moving in a straight line. So really what's happening here is gravity is just changing what it means for a path to be straight. This guy thinks he's moving in a straight line. This guy thinks he's moving in a straight line. We would disagree because this looks curved to us, but gravity changes what it means for a path to be straight. And this is something we're actually quite familiar with. And you'll excuse me, everybody probably knows this, but we're familiar with this anytime we do air travel. You know, if you want to fly, say, from Chicago to London, you always fly over Greenland, which if you think about it is kind of weird. The straight line between Chicago and London is this, it's not this. And of course we know why airlines choose to go over Greenland. And airlines aren't stupid, they want to make as much money as they can. That means using the least amount of fuel as they can, and that means taking the shortest distance path to the extent that they can. So this route appears curved and not optimal only because we just looked at the two-dimensional surface of the Earth, and we haven't accounted for the fact that the Earth is curved. Since if you look at the fact that the Earth is curved, you'll see that this weird path that goes over Greenland is actually the shortest distance between Chicago and London. Now, I want to mention something here. Our ability to see this, and this nice picture that we see, where we can say, oh yeah, obviously it's the shortest distance path because it's curved. The reason we can have this picture is because we can step away from the surface of the Earth, go into outer space and look back and actually see this curvature. And where this curvature is coming from is, we're saying the two-dimensional surface of the Earth is curved. And we're able to see that curvature because we can see what it's doing in a third direction. We can see that it's really a sphere living in three-dimensional space. If we were never able to go out in space and look back at the Earth, the only way we would be able to tell that the Earth was curved, just roaming around on the surface, would be by, going, looking at paths between different points on the surface of the Earth and measuring their distance and noticing that for some reason this one is shorter than this one. So that is how we would conclude, if we were just stuck on the two-dimensional surface of the Earth, that is how we would see the curvature. The only way we would see it is that the straight line paths would look weird. They would look weird. I bring this up because in our world, we live in a three-dimensional world, and if our three-dimensional space is curved, we can't do an analog of zooming out and actually seeing that curvature, because that would require putting our three-dimensional world into a bigger dimensional space. Good luck with that. I know I'm a string theorist, I'm supposed to be like, yeah, bigger dimensional space. but we're not really going to be able to do that. So the only way that we can detect curvature of the space in which we live is just by looking at the paths connecting objects and what the short distance paths are. Okay. So the path from Chicago to London is the analog of a straight path on a curved space. And we have given a name of this. It's called the geodesic path. And the only reason it appears non-minimal when we look at a flat surface is because we didn't account for the fact that the Earth's surface is curved. So the statement here with these two guys is that, well, this guy thinks he's moving in a straight line, this guy thinks he's moving in a straight line, so they must both be straight lines. They're both straight lines. It's just the fact that the sun being here has curved the space around it. So these are both straight lines, but the fact that this one, appears curved to us is because, or it doesn't appear straight to us, is because the sun is here introducing some curvature to the space. So this leads to the idea that gravity curves space. Notice that this conclusion, that gravity curves space, is a direct consequence of the equivalence principle, the statement that these two observers are essentially indistinguishable. It is, in some sense, the ultimate realization of the equivalence principle. Everything is affected the same way. So, okay. So matter curves space, the motion of free-falling observers is straight, but the space around them is curved, and so there's this usual picture where you think of a curved space as a big sheet of rubber stretched across the room, you throw a bowling ball in the middle, the bowling ball depresses it, and now you throw little marbles at it, and obviously the marble's going to come in, and when it gets to this region where it's depressed, it's going to shoot off. I'll emphasize again, the only reason this picture looks obvious and intuitive to us is because there's a third direction where we can see the rubber stretch. An observer that's just stuck living on the sheet of the rubber is going to have no way of detecting this curvature other than to just look at the paths that objects follow. So in our three-dimensional world, we're like the analog of this somebody just living in the sheet of rubber. Okay, so now I'm going to bring back a blast from the past, the first lecture, just to remind you that individual notions of space and time are observer-dependent. This is a diagram from the first lecture. I don't want to harp too much on it and go over it too much, just to remind you that the notion of spatial separation and time separation depends on the observer. Observers that move relative to each other see events happening in different orders, they see distances shifting around. So this is just to say that space and time are intimately connected. And we've known that since lecture 1, So gravity really can't curve space without also curving time in a sense. And don't ask me to give an intuitive explanation for what that is, because I don't have one, unfortunately. It's at this point where you start talking about weird things like curving time that you have to go talk to mathematicians. And that's what Einstein did. He got in touch with David Hilbert, who was one of the preeminent mathematicians of the early 20th century. There are about 1 billion things that carry Hilbert's name in the mathematics community. There are things called Hilbert spaces, Hilbert polynomials, Hilbert schemes, the Hilbert problems. Hilbert did a lot of stuff. But this is one of the other things that he did was he talked about differential geometry with Einstein, and they wrote down these things which I felt obliged to write. These are the Einstein field equations to describe the curvature of spacetime. So this R is some object that captures the curvature of spacetime, and this T is some object that captures energy and momentum and mass. And remember, in special relativity, mass is a version of energy. Energy and momentum can be moved into each other by going to different reference frames. So there's one object that captures it all. The energy momentum in curved space. And these are some fancy objects that describe curvature. And as with most fancy objects that mathematicians tell you about, if you actually try to write down what they are, they're a mess. So this little simple symbol stands for about 4 or 5 different terms that are really horrible. And then if you expand it out, you can learn probably what it is. It's a whole messy object, but they give it a simple name so you can write a simple looking equation like this. Do not be deceived. This is a very complicated set of nonlinear equations. It's very hard to solve. I think when Einstein first wrote them, he wondered if anybody would ever be able to find solutions. So he wrote them in 1915. Well, I forgot I wanted to mention this. There's this other term here, the cosmological constant term you can add, which is like background, it's like some sort of background constant energy for all the universe. There's a famous story where Einstein added this term, which would cause the universe to expand. At his time, nobody saw an expanding universe, so he said, oh, it shouldn't be there, big mistake, I'm done. And then, well, it turns out, no, the universe really is expanding, but it's expanding very slowly. This number is about 10 to the minus 120. And I don't know what's more amazing, that it's that small, or that astrophysical observations are precise enough to know that it's this small and also not zero. So it's incredibly impressive. To me, how they're able to determine this so precisely is kind of a black box. It's very, very impressive. If you could explain why this number is what it is, small and not zero, this is the deepest, most important problem in theoretical physics today, and you're shoo-in for a Nobel Prize if you figure that out. So. Well, I should say you have to figure it out, and then also convince everybody else that your reasoning is right. The second part may be the harder part. So I'm going to skip a bit on the metric tensor for time. It's very difficult to think about curved spacetime. So we use a version of spacetime diagrams that captures important features. So you remember, here's what we called the spacetime diagram before. This was supposed to describe all the events in space. An event here is happening at some position x and at some time t. So a path describes this path that an observer takes in spacetime. So an observer that sits in one place for all time would have a path that just goes up the t-axis, and every time they're in the same place. And the reason we like these diagrams is we scaled them so that light moved on diagonal lines, and so we could tell the difference between observers moving faster than light and slower than light. So it's a little bit annoying because almost all the interesting events are happening off the page. If this is about 1 second, well, okay, you go on for a second, but then after 2 seconds, you're all the way up here. So in order to visualize these things, we rescale distances so that all the points up here come back. And that results in a diagram like this, which is called a Penrose diagram. And well, here's Roger Penrose. Well, okay, the main property of a Penrose diagram is that light moves along diagonal lines, and it gives you an idea for a cartoon of space. So this is the Penrose diagram for flat space. If you ask somebody who does general relativity, draw a picture of flat space, they'll draw this. They'll just draw a diamond. And there are some constant time slices and whatever, but that's not really that important. So I said that Einstein's equations were very difficult, and Einstein thought that maybe nobody would ever solve them, so he wrote them in, 1915, 1916, so naturally, almost immediately, somebody found a solution. And that solution was found by Carl Schwarzschild. And here's a picture of his solution. Here's a Feynman diagram, or a Penrose diagram picture of his solution. And a couple things to point out. There's a diamond here, and when you see a diamond, you think that's a copy of flat space. There's a diamond here, that looks like a copy of flat space. And something interesting is nobody from this diamond can ever get to this diamond. Why? Well, this is why these diagrams are useful. The nice thing about these diagrams is light rays move on diagonal lines, which means observers have to move at a higher slope than diagonal lines because nobody can move faster than light. You can't move far in the x direction without going far in the t direction. So nobody can get from over here to over here without moving on a line that's got a smaller slope. So nobody can get from here to here without moving faster than light. And that's why these diagrams are interesting, because they allow us to see that, well, these are roughly two completely different parallel universes here that nobody can go back and forth between. Now, I put a rocket ship here, and this rocket ship is doing something a little bit troublesome. This rocket ship is passing into a region by where the singularity is. There's a singularity of the solution where the curvature becomes very large. And, well, these look like flat space, and this guy looks like he's in a bit of trouble. Because once you're in this triangular region here, you can't get back out. The only way to get out, if you move at the speed of light, you move on one of these diagonal lines. That's going to take you to the singularity. If you move slower to the speed of light, you just move up faster. The only way to get out is to move faster than the speed of light. So this guy is doomed to hit the singularity. There's nowhere else he can go. And, of course, this is just a picture of the thing we call a black hole. The first non-trivial solution to Einstein's relativity was this solution, the Schwarzschild solution, which described black holes. This line here is the thing, the event horizon. It's the line, it's the surface beyond which nothing, not even light, can escape. Even a light ray in here, a light ray is emitted from here, it'll move on a diagonal line. It can't get out. Excuse me, it's always stuck going to the singularity of the black hole. So this is the first non-trivial solution. It was a black hole, but I wanted to write this down because I wanted to point out that real black holes don't really look like that. Real black holes really look like this. A black hole, Schwarzschild solutions, a black hole is a geometry that's really existed from all time, has some special initial conditions with a white hole. Real black holes are formed when matter comes in and collapses, and this is a picture of that. The shell of matter comes in and it collapses and makes a singularity up here, and then here's the event horizon, and here's our person running into trouble. The reason I wanted to draw this picture is to point out there's no parallel universe here. These weird things like parallel universes and wormholes, they come up in very specialized geometries that you're really never going to make in the real world, so that all belongs to the realm of fantasy land. There's no parallel universes or anything like that. Okay. So this is all great. We've studied curved geometry. We've seen equivalence principle in curved geometry, but now I just want to come back at the end to the fact that something should really bother us. The equivalence principle was a fundamental principle that led us to curved space-time, but we never came back to this. Newtonian gravity, positive action at a distance, and that was inconsistent with special relativity, and I want to come back to that. Now, action at a distance had a natural solution to electromagnetism. In electromagnetic theory, you also could have said that the force between two charged particles was felt instantaneously across large distances. But when we properly formulated electromagnetic theory, we replaced that with the idea of exchange. We said, if an electron is sitting here, as another electron is moving along, that electron changes the electric field that everybody feels. And so we'll eventually change the force the sky feels. But it changes the electric field by sending ripples of electric field, electromagnetic waves. And this guy doesn't feel the force, the change in force from this guy until these waves actually get there. So this is nice because it keeps information from traveling faster than light. This guy communicates with this guy, but by sending ripples of electromagnetic waves. And that's how action at a distance happens. And I'll remind you, this is just a macroscopic version of the process of photon exchange that we've been talking about in all the particle physics lectures. This is two electrons interacting by exchanging a billion photons, which build up to make a big electromagnetic wave. The microscopic version of that is this particle exchange picture that we know from the Standard Model. Now in gravity, if I have this picture of curved space-time and I take a massive body and I have it move in space-time, what's going to happen? Well, as it moves, it's going to send ripples in space-time. And this guy is not going to know anything about this observer until those ripples get there. So curved space-time gives us an idea of where the ripples travel. And these ripples have a name, they're gravitational waves. They're also solutions to Einstein's equations. Even though Einstein's equations are very complicated, there are simple wave solutions. They're gravitational analogs of electromagnetic waves. And they move at the speed of light, so they carry the information about the new massive body to us. So I want to ask two questions in the last 5 minutes. I still have 5 minutes. What would a gravitational wave look like, and do they exist? Well, here's the canonical picture of what a gravitational wave does. It stretches, if we're standing still, and a gravity wave passes through us, it's going to stretch and contort space-time as it goes. So the canonical way to draw that is to say you have a hoop, and you look at what the gravity wave does to the hoop, and the gravity wave is going to deform the hoop this way, and then that way, and this way, and then that way, and so on. I found actually a better cartoon on the internet somewhere of what a gravity wave would do to an unsuspecting physicist who was standing there cheering for it to come along. First, it will contort the physicist in these directions, stretch it vertically, and then stretch the physicist horizontally. So that's really what a gravity wave does. It's really warping the distances that we measure in space-time. Now, do we know that gravitational waves exist? There's indirect evidence, and that indirect evidence comes from binary star systems, which emit very strong gravity waves. So you imagine two very massive stars rotating around each other, and they send off these big ripples. Now, these ripples aren't big enough that we've been able to observe them on Earth, but Pulse and Taylor were able to show that the orbital period of one of these binary systems actually decreases with time. Now, why is the orbital period decreasing? It's decreasing because the system is losing energy. Why is it losing energy? Well, it takes energy to make all these ripples. So these stars these binary stars are rotating. They're emitting energy in the form of gravitational radiation. And these guys showed that the rate at which they're losing energy is equivalent to the rate that that energy should be emitted in gravitational waves. So it's an indirect confirmation of gravity waves, and it was strong enough that they got a Nobel Prize for it. The direct detection of gravity waves is underway. There are experiments like LIGO, this is a slide from the first lecture, that are using these giant interferometers, the 4-kilometer interferometer arms, that are very sensitive to small changes in the length of one arm relative to the length of the other arm. They haven't seen anything yet, but they're just now getting to sensitivities where they can start seeing things, and we hope to get good news soon. And finally, I want to close on this note. Since we have these gravity waves, and since the gravitational interaction happens through the exchange of gravity waves, it's now a trivial matter to quantize gravity. We do what we did with every other force of nature. We take the idea that the gravity wave will have the smallest piece, a quantum. In this case, we call it a graviton. It's just like a photon in some sense. The photon is the smallest packet of energy in an electromagnetic wave. A graviton is the smallest packet of energy in a gravity wave. So we introduce this particle, and we introduce a force that's mediated by the exchange of this particle, and we're done, right? Well, I put if only life was that easy here, because life is not that easy. This doesn't work quite as nicely as in the standard model, and doesn't address all of the odd problems of gravity. In some sense, I'm glad life's not that easy, because it makes life more interesting. But quantizing gravity is a much harder problem than this. And that's my advertisement for next time, which is a whole hour on why quantum gravity is such a hard problem. And then that's before I tell you that string theory is a great solution, and you're supposed to go, yay, well, like string theory. Well, I don't want you to do that. I want you to come away with an understanding of what the problems are with quantum gravity, and form your own opinion about the ability of string theory to provide an answer to them. So I'll stop there. Here's the summary.